In the last screencast, we were beginning to answer the question, what holds a nucleus together? And the reason that's a question, or a mystery, or intriguing, is the fact that the nucleus has all these protons, and all these protons are positively charged, so they should repel each other. So how in the world can a nucleus for a given atom be stable and yet have all of these protons repelling each other? And to some extent, we said that by having neutrons in between the protons, it helps to mitigate or lessen the effect of the proton-proton repulsion. However, there has to be an awful lot more going on than just that. And what's going on, the way that we've answered the question, is by recognizing that when you add up the mass of the individual nucleons in any given nucleus, and then you compare that to the nucleus mass itself, the two numbers aren't the same. The sum of all the individual masses of protons and neutrons is always greater than the mass of the nucleus itself. And so the question is, what happened to the missing mass? Is it true, perhaps, that matter can be created or, in this case, destroyed? And the answer is no. We need to remember matter is just one form of energy. And that comes from Einstein's famous equation, E equals mc squared. This energy is called the nuclear binding energy. When you add up the mass of the individual nucleons, the particles on the left side of the arrow, that mass will be greater than the mass of all the nucleons on the right side of the arrow in any nuclear equation. The differences in mass is called the nuclear mass defect. And if you plug that nuclear mass defect into the equation E equals mc squared, you can calculate the energy that's involved in holding the nucleus together even though the protons are repelling each other. At the very bottom of this page, you will notice that in a deuterium nucleus, there's a deuterium nucleus right there. It's got two nucleons, one proton and one neutron, so it's an isotope of hydrogen. That if you had a hydrogen-hydrogen bond between two hydrogen atoms, each with only one proton, that covalent bond represents 436 kilojoules of energy. But if you've got the nuclear mass defect energy, the energy holding a proton and a neutron together inside a nucleus, which is much, much smaller, now you're talking about 215 million kilojoules of energy per mole, 500,000 times larger. Now this page shows us how we do that calculation. Again, we have to find the missing mass. And because this is the mass in the nucleus, we call this the nuclear mass defect. Now, it's not defect in the sense of being defective. It's defect in the sense of it's missing. And that missing mass has been turned into energy. Now, we know an awful lot about the mass of nuclei of all kinds of atoms thanks to the mass spectrometer. Very, very sensitive and enables us to get a lot of significant digits in finding the masses of these nuclei. If we didn't have a lot of significant digits, we would never notice that there was a missing mass, because this missing mass doesn't show up until about the 4th or 5th or 6th decimal place after the decimal point. Now, the calculation that is done here for the deuterium, which was mentioned in the previous page, shows that if you look at the mass of your deuterium, one proton plus one neutron, H2, and then you look at the mass of a proton and the mass of a neutron, you'll notice we get this nuclear mass defect of 0.00239 grams per mole. We would convert that into kilograms so that our dimensions will work out when we plug it into E equals mc squared. That's equation 23.1. Your delta M is the nuclear mass defect. This comes from Einstein's 1905 theory of special relativity, not to be confused with this theory of general relativity having to do with gravity. So it's a little over 100 years old. Now, in physics, we usually don't talk about the energy to hold a nucleus together in terms of kilojoules. We usually talk about this energy in terms of mega electron volts, where voltage is the potential energy per charge of an electron. And that's something for next year. And for the sake of comparison, we usually do this per nucleon. We divide by the total number of nucleons, which in this equation, if you look at the left side of the arrow or the right side of the arrow, you have a total of 2 nucleons, a proton and a neutron. And so when you compare all of the binding energies, the energies holding the nuclei together for all your different elements and all their isotopes, to have a fair comparison, since some isotopes have way more nucleons than other, we always divide by the total number of nucleons. And that's the binding energy per nucleon. It's that last step of dividing by the number of nucleons that students often forget to do in a homework or on a test. Now, the last thing on this page, the greater the binding energy per nucleon, the more stable that nucleus will be. If you have an awful lot of energy holding the nucleus together, it's going to make for a stable nucleus. Here is another classic graph in nuclear chemistry. You'll notice the yellowish, orangish rectangle. That is this region of greatest stability. That's the high point on the graph. That's where you have about 9 times 10 to the 8th kilojoules of binding energy per nucleon, holding the nucleus together. And you'll notice that whether you go left or right from that region of stability, you go downhill. You go downhill slowly towards the right and you eventually get to uranium, and you go downhill quite rapidly as you go down to helium and hydrogen. But in either case, what this graph tells us is that in order to become more stable, big nuclei need to lose some of their mass, and small nuclei like hydrogen and helium and so forth need to gain mass to become more stable. Well, big nuclei like uranium-238 or uranium-235 can lose mass, and one way is by splitting the nucleus, and another is by undergoing decay, radioactive decay. Small nuclei can become more stable by fusing together. So this graph anticipates the 2 ways to generate electrical energy and get the release of this binding energy. One is through fusion and one is through fission. And of course, nuclear fission is what we use in our nuclear reactors that generate electricity. And nuclear fusion is what we hope to someday be able to use to generate electrical energy. And as is often the case, back in the 1940s, finally in 1945, we used nuclear fission to create atomic bombs that abruptly ended World War II by decimating Hiroshima and Nagasaki. And today we have hydrogen bombs, fusion bombs, that are many times greater. And let's pray that they are never deployed in combat. But I should also mention that to talk about nuclear energy and nuclear weapons in the same paragraph is just as silly as talking about electrical motors or electrical light bulbs at the same time you're talking about electric chairs or electrocution. Two very, very, very different kinds of things. Here is a practice problem where you calculate the nuclear mass defect and you find out how much mass is missing when you create the nucleus. And that's the energy holding that nucleus together. And when you plug that mass, after converting it into kilograms, into E equals mc squared, where c is the speed of light in meters per second, you can find your kilojoules per mole, and then you would divide it by the total number of nucleons, which in this problem would be 12, because you've got 6 protons and 6 neutrons. And there's your binding energy in kilojoules per mole of nucleons. Now, how long does it take for an unstable nucleus to become stable? This is actually a rather complicated question because they don't become stable all at once. Frequently, an unstable nucleus becomes a little more stable by shooting off an alpha or a beta or a gamma or maybe a positron or a neutron. And that resulting nucleus is still unstable, and it too will undergo a nuclear decay, and again until finally, when you go through a decay series, you reach a stable isotope of lead. And each step of the way requires very, very different amounts of time. Now, when I talk about time, I don't mean the total time it takes for one nucleus to become another. And the reason we can't talk like that is because if we were to examine a particular nucleus, if that were possible, there's no way to predict when that nucleus will shoot off an alpha particle or a beta particle or whatnot. However, if we had a statistically large enough sample of nuclei, we can estimate how long it would take for about half of those nuclei to decay. And a good example would be imagine you had 1,000 pennies in a box. If you were to shake up 1,000 pennies in a box, you would estimate that approximately 500, give or take, would come up heads. And let's say you were to remove all of the pennies that came up heads. You would have approximately 500 pennies. Now you would shake all of those up and then take out the ones that came up heads, and about half of those would come up heads, give or take. And you would remove those. Well, if you keep doing that, half of a half of a half of a half, eventually, let's say you get to 1 penny. And you shake it up. Does it come up heads? Let's say it doesn't. Does that automatically guarantee that the next time you shake it up, it'll come up heads? No. Every single time you flip that penny or shake that penny, you have a 50-50 chance of coming up heads. You cannot predict when that last penny will come up heads. But you can estimate how long it takes for a large sample of pennies to come up heads. And that's the same as half-life in radioactive decay. If you have a large enough sample of nuclei, and sometimes we call that original number, n sub aught, your original number, you can estimate, or we can often measure, how long it'll take for half of those those nuclei to decay. And then we do half of a half and half of a half. And you get this graph, as you see at the bottom of the page, that asymptotically approaches the x-axis. So each half-life is the same length of time as every other half-life, until eventually you have too small a sample to be statistically reliable. And this amount of time for half of your sample to undergo decay and become more stable varies greatly. Anywhere from 4.5 billion years for something like uranium-238 to nuclei that you would measure their half-lives in the microseconds, in the millionths of a second. In nobelium, for example, if I had a handful of nobelium, in about 3 seconds, I would have half a handful of nobelium, and the other half would be whatever nobelium would decay into. And then after another 3 seconds, I'd have half of a half, and so forth. It's interesting that uranium-238 has a half-life of about 4.5 billion years, because many scientists estimate that the Earth was made 4.5 billion years ago. And any elements that have half-lives shorter than that, either those radioactive isotopes don't exist anymore because so much time has passed that they've all decayed away, or whatever of those isotopes does exist is the product of coming into existence as a result of one of these decays from uranium or plutonium or something like that. So all you have to do is count the number of half-lives. And you might remember we looked at this equation and we derived the equation for half-life way back when we were doing chemical kinetics, and we looked at zero order and first order and second order chemical reactions as they turn from reactants into products. And we had the same equation. And that equation is going to be derived here at the bottom of the page. And sadly, we don't have time to do the calculus to show this. It's based upon an original assumption, a beginning assumption, that the total number of nuclei that will decay will be proportional to the total number of nuclei that you start with. And then we introduce a decay constant, the letter K, in equation 23.3. We have the negative sign because this is going to be a decreasing amount of nuclei left to undergo decay as time goes on. And if we were to go through the calculus, and we do this in AP Physics, I think I gave it to you on your handout, we end up with the half-life, equation 23.6, the half-life equals the natural log of 2.693 divided by the decay constant K. And so every radioactive nuclei has its own half-life and its own decay constant. We can also use equation 23.5, just above it, to look at the ratio of the number of particles we would have compared to the original number, A sub aught, in a sample over time. N divided by N sub aught to get that fraction. And A, is activity, not the number of nuclei. N is the number of nuclei. So if we look at example 23.6, if we have a sample of radon-222, it has an initial decay rate of alpha particles of about 70,000 decays per second, 7 times 10 to the 4th decays per second. And we know that from experience, from gathering your radon-222 and measuring its activity with a Geiger counter or something. And after 6.6 days, we find that its activity is 2.1 times 10 to the 4th. So it's a little bit less. We can say, well, what is the half-life of radon-222? Well, we can kind of estimate that before we look at the next page. After one half-life, we would expect to have half of 7. So after 6.6 days, we would expect to have 3.5 times 10 to the 4th. After another 6.6 days, we would expect to have half of a half of 3.5, which is about 1.75, a little bit less than this 2.1. So we would predict, we could estimate what the half-life of radon is going to be. It's going to be less than the 6.6 days. And sure enough, when we do the calculations here, we see that it's 3.8 days is the half-life. Now, of particular interest is radiocarbon dating. Radiocarbon dating refers to using a very rare, small percentage occurrence of radioactive carbon, carbon-14, that undergoes natural radioactive decay to figure out how old things are that have carbon in them. And here's how it works. In the upper atmosphere, we have cosmic particles coming in from stars, especially the sun, including neutrons. And when a neutron strikes a nitrogen-14 atom, and we have lots of those because you have diatomic nitrogen gas making up 79% of the atmosphere. When a neutron were to strike one of those atoms, it gets absorbed, it turns into carbon-14 and shoots out a proton. Now that carbon-14 is unstable, it's radioactive. You might look at the periodic table and know that most carbon is carbon-12. 6 protons, 6 neutrons. There's some amounts of carbon-13, 6 protons, 7 neutrons. And carbon-14 is formed in the upper atmosphere. And of course, carbon-14 then becomes incorporated into carbon dioxide. Carbon dioxide then is used in photosynthesis to create the green in plants for plants to grow. And animals that eat plants and animals and humans that eat animals that eat plants and humans that eat plants, we pick up some of this carbon-14 in us. So you are naturally radioactive. The food that you eat is naturally radioactive. The ground that you're walking on is naturally radioactive. And our bodies are used to that. And small amounts of this is just naturally repaired all the time. Now, when we measure the natural radiation due to carbon-14 in a 1 gram sample of carbon, we get about 14 disintegrations per minute with our Geiger counter. Which, if you're thinking ahead, would mean if we had a sample of carbon, a 1 gram sample of carbon that we found in a fireplace way back in a cave of old ashes, or maybe some vegetable residue in the bottom of some old ceramic pot that's broken that was dropped down a well or back in a cave somewhere, or maybe we found an ancient bone and we extracted 1 gram of carbon. Anytime we find something that's only 7 disintegrations per minute instead of 14, that means this sample is about 1 half-life old. What is the half-life of carbon-14? Turns out that the half-life of carbon-14 is 5,730 years, which would make this sample 5,730 years old. Now, there's a lot of things that have to be taken care of when you make these kinds of tests, and there are some assumptions that are involved. For example, one assumption that we make is we assume that the rate of radioactive decay, that is to say the half-life of a given nucleus, doesn't change. And we have never figured out how to speed up or slow down or stop or make happen a radioactive decay of a particular nucleus. We don't know how to do that. Now, it might happen someday in the future that we'll know more about the nucleus and its infinitely complex and amazingly designed structure. Because after all levels of God's creation become increasingly designed and complex and amazing. But when we get to that level, we might be able to figure it out, how to make decay speed up or slow down or stop it. And so there are some Nobel Prizes waiting to happen here. Now, another thing we have to keep in mind with carbon-14 dating is that it's only good if the substance has carbon in it. Carbon that comes from formerly biologically living things. Another thing we have to assume is that this 14 disintegrations per minute was the same a long time ago as it is today. This is different than talking about its half-life. The half-life doesn't seem to vary, but the amount of carbon-14 in our atmosphere actually has fluctuated a little bit up and down over time. And we know this from lots of different proxies, such as tree rings, dendrochronology, tree rings, and also looking maybe at dust and pollen and so forth captured in ice cores that go thousands of feet down into glaciers and ice masses and so forth. And so we can see that there have been variations of cosmic radiation which cause variations in the disintegrations per minute of carbon-14. I think the variations seem to be somewhere around 12 or 12.7 to 14, if I remember things that I've read in the past correctly. So you have to take that into consideration. Another thing that you have to assume, and these are all possible test questions, remember, is that after so many half-lives, if you remember that curve that we were just looking at, that went down and down towards the right until it began to level off near the x-axis, that after 4 or 5 or 6 half-lives, you do not have a statistically large enough sample of carbon-14 anymore to reliably use in determining the date or age of something. So at the very high end, maybe carbon-14 can be used to date things going back 50,000 years. Some people might push it a little bit more. Some people are a little bit skeptical at that number. But after about 4 or 5 half-lives, since you start off with so little to begin with, you really don't have enough anymore. It's like trying to predict when a penny is going to come up heads. How many times you flip it will that take? Now, we use this all the time, and we have corroborating evidence to support it, because we can look at things in the last 20, 25,000 years, such as tree rings, such as dust and pollen from ice cores, and it matches up pretty well. And here's a graph, by the way, that shows the variation in carbon-14 due to the influx of cosmic particles that creating carbon-14 in the atmosphere. It does fluctuate a little bit. So we can get some pretty accurate dates. Now, of course, the older something is, the more assumptions are involved, the more you're depending upon the purity of your sample in the sense of stuff not leaching in or stuff not leaching out. But certainly in the short term, you can get some pretty reliable dates. And here's an example of that with the Iceman, whose age was estimated to be 5,300 years ago, before he tragically got frozen up in a glacier high in the Alps. What he was doing up there, of course, we have no way of knowing. It's all a matter of calculating the ratio of the decays per minute down here compared to an estimate of your natural decay that something would have when it's alive. Now, I should mention that as long as something is alive, the decays per minute stays constant. Because when something is alive, you may have noticed this, I hope, something that is alive keeps bringing in carbon, either through photosynthesis if it's a plant, or by eating it, in eating hydrocarbons of some type, and carbohydrates for animals. And you keep getting rid of it. Not only do you exhale carbon dioxide, but you have the natural decay going on. So the level of carbon-14 in a living thing stays constant as long as that organism is alive. But as soon as the organism dies, it stops bringing in carbon-14, but it doesn't stop having the existing carbon-14 decay. And that's why the decays per minute goes down. And I'm going to stop right there for the time being, and we'll finish the chapter next time.